Hello, dear friend, and welcome to the Sleepy Science Channel. Tonight, prepare to embark on an extraordinary odyssey, a journey that will carry us far beyond the familiar territory of the atom, plunging us into the enigmatic depths of the quantum realm. Here, at this subatomic scale, the very fabric of reality seems to unravel, challenging our most deeply held assumptions and rendering the seemingly impossible not just possible, but commonplace. This isn't merely a tale of scientific discovery. It's an exploration of the very boundaries of scientific inquiry itself, a quest to understand the fundamental nature of existence. So settle in, make yourself comfortable, and let us begin. Imagine, if you will, the world around you shrinking, slowly diminishing in size, receding beyond the reach of even the most powerful microscopes ever conceived. At this infinitesimal scale, everything you once perceived as solid and immutable, the sturdy table, the breathable air, even your own resilient skin, is revealed to be, in reality, an almost incomprehensible expanse of empty space. Once upon a time, atoms were revered as the ultimate indivisible building blocks of all things, the fundamental units from which the entire universe was constructed. But as scientists, driven by an insatiable curiosity, peered deeper and ever closer, they stumbled upon a hidden reality, a secret domain, the quantum world, where atoms and the subatomic particles that dwell within them behave in ways that utterly defy our everyday experiences and expectations. In this strange and wondrous domain, the comforting certainty of the macroscopic world dissolves away. Particles no longer possess definitive positions or fixed speeds. Instead, they exist as ephemeral waves of probability, forever dancing in a realm of uncertainty and chance. This is a universe governed not by the predictable laws of classical physics, but by the capricious whims of probability and subtle, hidden rhythms. A universe far removed from the solid, tangible objects we can touch and see. What indeed does it truly mean for something to exist simultaneously as both a particle and a wave? How can an entity be present in multiple locations at once, or perhaps even more perplexing, in no specific location at all? These profound mysteries beckon us to delve deeper, to contemplate the invisible laws that intricately shape all that exists in this vast and complex cosmos. With this spirit of quiet curiosity as our guide, let us now begin our exploration of the atom's very structure, tracing the winding path of scientific discovery from the earliest, most rudimentary models to the groundbreaking revelations that ultimately unlock the door to the revolutionary field of quantum mechanics. But long before the advent of modern science and its sophisticated tools, the concept of the atom began as a simple, elegant idea born in the crucible of ancient philosophy. Thousands of years ago, the great Greek thinkers, contemplating the nature of reality, envisioned tiny, uncuttable pieces of matter which they christened atomos, meaning quite literally, indivisible. These atoms, they believed, were the smallest, most fundamental components of the world, solid, unbreakable, and eternal building blocks that, in countless combinations, gave rise to everything we perceive around us. It was a bold and audacious idea, conceived to explain how the complex and ever-changing world could possibly arise from unchanging, basic components. This ancient vision was driven less by rigorous experimentation and more by the power of imagination and reason. It represented an early attempt to impose order on the apparent chaos of nature, to discover a stable foundation beneath the ever-shifting forms of life and matter. Yet these early atoms, conceived in the minds of philosophers, bore little resemblance to the subatomic particles that modern science would ultimately uncover. They were static and simple, lacking the inherent mystery and strangeness that characterized the quantum world. They lacked, crucially, the layers upon layers of complexity that quantum physics would later reveal. Over the centuries, as scientific tools and experimental techniques became increasingly sophisticated, scientists began to unravel the true nature of the atom. Instead of being tiny, solid spheres, atoms were found to be composed primarily of empty space, containing even smaller particles, electrons, whirling in a complex dance around a dense central nucleus comprised of protons and neutrons. And crucially, these subatomic components did not behave like solid objects at all. They moved in waves exhibiting a bewildering duality, sometimes acting like discrete particles, and sometimes like ethereal waves of possibility. The transformation from ancient philosophical speculation to modern quantum science is a remarkable testament to the relentless human drive to understand the universe. It teaches us that reality can be far more subtle, complex, and mysterious than our initial superficial impressions might suggest. The atom, once thought to be indivisible and simple, is now recognized as a gateway to a universe brimming with probabilities, uncertainties, and a profound, almost ineffable beauty. A universe that lies hidden quietly beneath the surface of everything we know. In the early 19th century, the story of the atom took a decisive turn with the arrival of John Dalton, a brilliant British scientist who injected a fresh dose of clarity and rigor into the evolving concept of the atom. Dalton, building on the ideas of his predecessors, proposed that everything in the observable world is composed of tiny, indivisible particles he called atoms, minuscule spheres that combine in specific fixed ratios to form different substances. This was a monumental step forward, a bold stride towards the creation of modern chemistry. Dalton's theory provided scientists with a concrete framework, a tangible model for explaining the behavior of matter. Dalton's atomic theory posited that atoms of a particular element were identical in mass and properties and distinctly different from atoms of other elements. He envisioned these atoms as solid, indivisible balls, each possessing its own unique weight and identity. Chemical reactions, in Dalton's view, were simply rearrangements of these atoms, combining and separating without undergoing any fundamental change themselves. While Dalton's model was remarkably simple, it was also exceptionally powerful. It helped explain why substances combine in fixed proportions, for example, why water is always composed of 2 parts hydrogen and 1 part oxygen. It laid the foundation for understanding chemical reactions as the physical mixing and separation of atoms, rather than some mysterious transmutation of matter. Yet, despite its groundbreaking usefulness, Dalton's vision had its limitations. Atoms, as it turned out, were not truly indivisible. Later discoveries revealed the existence of subatomic particles, electrons, protons, and neutrons, residing within the atom, fundamentally altering the very definition of what an atom actually is. Still, Dalton's work marked a pivotal moment in the history of science. It successfully bridged the gap between ancient philosophical concepts and empirical experimental science, transforming a centuries-old concept into a testable predictive theory. His vision of atoms as tiny, solid particles inspired generations of scientists to probe deeper, moving from the concept of indivisible spheres towards the strange and wondrous quantum world that lay beneath. This gradual shift from simplicity to complexity perfectly mirrors the unfolding mystery of the atom itself. From solid, immutable blocks to dynamic, complex systems teeming with unseen motion and uncertainty. At the close of the 19th century, the seemingly simple idea of the atom as a solid, indivisible sphere faced a profound challenge from a wave of new and groundbreaking discoveries. J. Thomson, a brilliant English physicist, conducted a series of experiments that revealed that atoms were not as indivisible as previously believed. In 1897, Thomson made a monumental discovery, the electron. This tiny, negatively charged particle was found to be far smaller than the atom itself. Thomson's breakthrough stemmed from his meticulous study of cathode rays, streams of particles propagating inside vacuum tubes. He discovered that these rays were composed of particles lighter than any known atom, particles he named electrons. This was the first glimpse into the complex inner world of the atom, definitively proving that it was composed of smaller constituent parts. The discovery of electrons implied that atoms were not solid, indivisible units, but rather possessed an internal structure. This revelation, in turn, raised a host of new and challenging questions. If atoms contain negatively charged electrons, what balances out their charge? And how are these subatomic particles arranged within the atom itself? Thomson proposed the plum pudding model to address these questions. He envisioned the atom as a sphere of positive charge, with electrons embedded within it like tiny raisins in a plum pudding. While this model was ultimately proven to be incorrect, it was nonetheless a vital step forward in our understanding of atomic structure. Soon after, other subatomic particles were identified: protons carrying a positive charge and neutrons, electrically neutral but contributing significantly to the atom's mass. These discoveries revealed the atom to be a complex system, a miniature universe of charged particles interacting in a delicate and intricate balance. This burgeoning knowledge fundamentally transformed the fields of chemistry and physics, demonstrating that the building blocks of matter were themselves composed of smaller parts, moving far beyond the simplistic notion of Dalton's indivisible spheres. The atom was no longer a static object, but rather a dynamic system, a complex puzzle waiting to be solved. As we continue our journey, we will explore how these early findings led scientists deeper and deeper into the strange, probabilistic world of quantum mechanics, where particles behave in ways that utterly defy classical logic. Around 1911, Ernest Rutherford and his dedicated team embarked on a mission to probe the internal structure of the atom through a brilliantly conceived experiment. They directed a beam of tiny, positively charged particles, known as alpha particles, at an ultra-thin sheet of gold foil. According to the prevailing plum pudding model of the atom, these alpha particles should have passed straight through the gold foil with minimal deflection, as the positive charge was thought to be evenly distributed throughout the atom. However, what Rutherford and his team observed was nothing short of astonishing. While the vast majority of alpha particles did indeed pass through the gold foil with little or no deflection, a small but significant fraction were deflected at surprisingly sharp angles. Some particles even bounced back towards the source. This unexpected result suggested that the positive charge within the atom was not diffuse, but instead concentrated in an extremely small, dense region. Based on these observations, Rutherford proposed a revolutionary new model of the atom. He suggested that the atom's positive charge, and almost all of its mass, resided in a tiny, dense nucleus at the atom's center. The electrons, he proposed, orbited this nucleus much like planets orbiting a sun, albeit on an unimaginably smaller scale. This nuclear model of the atom completely overturned the plum pudding idea and introduced a whole new way of understanding atomic structure. The discovery of the nucleus explained why most alpha particles passed through the gold foil unaffected. The atom was, in reality, mostly empty space. However, Rutherford's model also introduced new and perplexing questions, most notably, how do electrons remain stable in orbit around the nucleus without spiraling into it due to the attractive electromagnetic force? Classical physics simply couldn't provide an adequate answer. Rutherford's experiment was a pivotal moment in the history of science, marking the birth of modern atomic physics, revealed the hidden, dense core within matter, and set the stage for the quantum mechanical revolution that would soon follow, where certainty gave way to probability, and the familiar rules of the visible world no longer applied. This glimpse into the atom's heart invites us to continue looking closer, deeper, and with ever more nuanced perspective into the world's smallest and most mysterious building blocks. Building upon Rutherford's groundbreaking discovery of the atomic nucleus, Niels Bohr introduced a new and influential vision of atomic structure in 1913. His model proposed that electrons do not simply orbit the nucleus randomly, but instead move in specific, stable paths or shells, reminiscent of planets circling the sun at fixed distances. This idea was revolutionary, primarily because it introduced the concept of quantized energy levels. Bohr proposed that electrons could only occupy certain allowed orbits without radiating energy and spiraling into the nucleus. He suggested that electrons could jump between these fixed orbits by absorbing or emitting discrete packets of energy called quanta. This explained the distinct lines observed in atomic spectra, the unique patterns of light emitted or absorbed by elements. Each line corresponded to a specific electron transition between energy levels. While Bohr's model worked remarkably well for hydrogen, the simplest atom, it struggled to explain the behavior of more complex atoms. Nonetheless, it marked a crucial step toward quantum theory by blending classical ideas with new quantum-based rules. The planetary analogy provided a comforting and intuitive image, electrons circling the nucleus in neat, well-defined orbits. But the true quantum world would ultimately prove to be far more mysterious, subtle, and less visually intuitive. Still, Bohr's insights paved the way for later developments, including wave mechanics and the probabilistic interpretation of electron behavior. Bohr's model also hinted at a deeper principle, that nature's smallest components do not follow continuous classical motions, but instead move in discrete steps governed by fundamental constants. This was a profound shift from the classical worldview, inviting us to reconsider the very nature of matter and energy. With Bohr's planetary atom, the door to quantum mechanics swung open wider, beckoning us to explore the subtle, strange dance of particles at the heart of all things. Bohr's planetary model represented a groundbreaking step in our understanding of the atom. However, it soon became clear that the classical physics of the 19th century couldn't fully explain the strange and often counterintuitive behavior observed at atomic and subatomic scales. As experiments delved deeper into the quantum realm, scientists encountered phenomena that defied the familiar rules of motion, energy, and measurement. One early challenge arose from the photoelectric effect, where light shining on certain metals causes them to eject electrons. Classical wave theories of light predicted a gradual increase in electron energy with increasing light intensity. But experiments revealed that electrons were only emitted when the light reached a specific frequency, suggesting that light behaved as discrete packets of energy, or quanta. This insight, introduced by Albert Einstein in 1905, helped launch quantum theory. Around the same time, Max Planck proposed that energy is quantized, emitted or absorbed in fixed amounts, to explain how hot objects radiate light. These ideas shattered the classical notion that energy changes were smooth and continuous. Then came the unsettling wave-particle duality, where particles like electrons exhibited properties of both waves and particles. Louis de Broglie suggested that electrons possess a wave-like nature, and experiments soon confirmed this, revealing interference patterns typical of waves. This duality undermined the classical picture of particles as tiny billiard balls moving predictably. Werner Heisenberg's uncertainty principle further challenged classical determinism. It revealed fundamental limits on how precisely we can simultaneously know certain pairs of properties, such as a particle's position and momentum. This uncertainty isn't due to measurement flaws, but is an intrinsic feature of nature. These developments culminated in the creation of quantum mechanics, a mathematical framework describing probabilities and uncertainties rather than fixed trajectories. Classical physics gave way to a world where observation, chance, and wave functions govern the tiniest scales. This new quantum view unsettled many, but it also opened a window into the deep structure of reality, inviting us to reconsider what it means to truly know the universe. Let's pause here and explore one of the most intriguing and fundamental concepts in quantum mechanics: wave-particle duality. At the heart of the quantum world lies a surprising truth. Entities like electrons and photons don't fit neatly into classical categories. Sometimes they behave like particles, small and localized. Other times they act like waves, spreading out and interfering with themselves. This dual nature was first glimpsed in experiments with light. For centuries, light was considered a wave, responsible for phenomena like diffraction and interference patterns. Yet the photoelectric effect revealed that light also behaves like a stream of particles, quanta of energy called photons, each carrying a specific amount of energy. The concept took a bold leap when Louis de Broglie proposed in 1924 that not just light, but all matter, including electrons, could exhibit wave-like properties. This idea was revolutionary. It suggested that tiny particles might have an associated wavelength influencing how they move and interact. Experiments soon confirmed this duality. In electron diffraction experiments, electrons fired through thin crystals produced interference patterns, clear signatures of wave behavior, something unimaginable if they were simply tiny solid particles. Wave-particle duality challenges our classical intuitions. How can something be both a particle and a wave? The answer lies in the probabilistic nature of quantum mechanics. Instead of having definite positions and velocities, particles are described by wave functions, mathematical expressions encoding the probabilities of finding them in various places. This dual behavior isn't just a curiosity, it lies at the core of quantum technology. From electron microscopes to semiconductors and lasers, understanding wave-particle duality allows us to manipulate the quantum world in ways that power modern life. As we continue, we'll explore how this duality shapes atomic structure and the mysterious rules governing the tiniest parts of reality. One of the most striking demonstrations of wave-particle duality is the famous double-slit experiment, which has captivated physicists for over a century. In this experiment, a beam of light, or even particles such as electrons, is directed toward a barrier containing two very narrow, closely spaced slits. Behind this barrier, a detection screen records where the light or particles land. If particles behaved like tiny solid bullets, we would expect to see two bright spots on the screen corresponding exactly to the two slits. But instead, what appears is a series of alternating bright and dark bands known as an interference pattern. This pattern is a clear signature of wave behavior created when waves overlap and interfere, amplifying in some places and canceling out in others. What makes yet as even more it reveals this in the it tells the act this print it reminds us that reality is not a simple clockwork mechanism but a dance of possibilities. Heisenberg's uncertainty principle has profound implications. It means that the universe itself has a built-in limit to predictability, setting a boundary for the exactness of measurement and knowledge. This uncertainty isn't just theoretical, it influences how atoms bond, how particles interact, and underpins the stability of matter. Understanding these limits helps explain why the quantum world feels so strange and counterintuitive, yet also why it is so rich and full of surprising phenomena. It invites us to accept a universe where certainty is replaced by possibility and where the act of observation plays a central role in shaping what we know. One of the most important tools for understanding the quantum world is Schrödinger's wave equation, developed by Erwin Schrödinger in the 1920s. This mathematical equation describes how the quantum state of a particle, such as an electron, changes over time. Rather than picturing electrons as tiny billiard balls moving along fixed paths, Schrödinger's equation treats them as waves, waves that spread out and interfere, creating patterns of probability. These probabilities aren't just abstract ideas, they form what we call probability clouds, or orbitals, regions around an atom's nucleus where the electron is most likely to be found. Unlike the precise orbits in classical models, these clouds give a fuzzy, ever-changing shape to where electrons can exist, reflecting the uncertainty and fluidity of the quantum realm. Instead of saying the electron is here, quantum mechanics tells us it's more accurate to say the electron has this likelihood of being here. Schrödinger's equation helps calculate these likelihoods, revealing the complex and beautiful shapes that electrons inhabit. This concept fundamentally changes how we understand matter's building blocks. Atoms aren't tiny solar systems, but rather dynamic, probabilistic systems where electrons blur in space, guided by the mathematics of waves. The wave equation connects the unseen quantum behavior with measurable properties, making it central to modern physics and chemistry. By imagining electrons as probability clouds, we embrace a world where certainty gives way to possibility, a quiet dance of existence that defies everyday intuition yet shapes everything we see around us. In quantum mechanics, the idea of a quantum state is fundamental. It describes all the information we can know about a particle or system at a given moment. But unlike in classical physics, where an object has a definite position or speed, a quantum state allows for something far more mysterious: superposition. Superposition means that a particle can exist in multiple possible states at once. For example, an electron might be in a blend of different locations or energies simultaneously, not one or the other, but both at once. It's only when we measure or observe the particle that this blend collapses into a single outcome. This concept challenges our everyday experience. We're used to things being in one place or having one property.